Welcome to the Deep Dive, the place where we take complex, cutting-edge technology and, well, we break it down into the most essential, fascinating nuggets of knowledge.
And today, we are tackling a big one.
A really big one. A system that many engineers, I think, rightly regard as a huge milestone in distributed computing. Google's Spanner.
Right. And this isn't just, another step up in database design. This was a fundamental attack on the problem of global data synchronization. A successful one at that.
I think that's the key. Spanner is basically Google's attempt to reconcile two things that seem like they shouldn't be reconcilable.
Massive scale and absolute consistency.
Exactly. For years, the consensus was, well, it's a trade-off, right? If you wanted a system to operate across continents, we're talking hundreds of data centers, millions of machines, you just had to settle for eventual consistency.
You had to. You use systems like Bigtable or any of the other NoSQL variants. Spanner just... It shattered that idea completely.
There's a phrase we really need to zero in on today, and that's external consistency. It's such a stringent guarantee. It's way beyond simple sequential consistency. What it means is that the ordering of transactions inside the database, it perfectly matches the real-world, actual, temporal ordering of those events.
So if I commit transaction A in New York...
Right, and then, say, 3 seconds later, you start transaction B in London, the system guarantees, absolutely guarantees, that A's timestamp will be strictly smaller than B's.
Which should be impossible. I mean, that kind of strict global ordering, with the speed of light and the fact that clocks are never perfectly in sync, it just shouldn't work.
But the need for it was intense. I mean, you look at their history. Bigtable gave Google scale, sure, but a lot of their internal apps were moving to systems like Megastore.
Because they needed real transactions. They needed strong guarantees, complex schemas that could evolve, and crucially, synchronous replication. Spanner was built specifically for that demand.
It gives you the best of both worlds. A temporal, multi-version, schematized database that, operates at a planetary scale.
And that ambition, I think that's what makes this so fascinating, building a globally synchronized system that still has to obey the laws of physics.
So that's our mission today. We want to understand the ingenious architecture, the core data structures, and the groundbreaking algorithms that let Spanner pull this off. We're going right to the heart of how they manage global time and run transactions across continents.
And that whole mission, it all comes down to one really novel feature.
True time.
The True Time API. It's the linchpin. It doesn't just give you a timestamp, it gives you a time interval, and it explicitly tells you, here's the clock's uncertainty.
So by bounding that uncertainty.
By bounding it, Spanner gets the geometric constraint it needs to enforce that strict, globally synchronized temporal ordering.
Okay, so let's unpack this. We're talking about a system that effectively imposes order on chaos, guaranteeing time itself across continents. And that's going to require an architecture built for just an unimaginable scale.
When we talk about Spanner, you really have to get your head around the sheer scope of it. This wasn't built for, a single web app. This was built to potentially run everything Google does. The design goal was millions of machines, hundreds of data centers, and trillions of database rows. This is infrastructure at the absolute top end of global scale.
It sounds less like a database and more like an operating system for global data.
That's a great way to put it. And it gets to that scale by doing what any good distributed system does. It shards the data, it breaks it up across lots and lots of small, consistent units.
And those units are?
At its foundation, Spanner is just a massive collection of Paxos state machines, thousands of them. Each one holds a shard of data, and these groups of replicas are spread all over the world.
And the replication isn't optional, it's baked in.
It's mandatory, and it's there for two very distinct reasons. First is global availability. You need to be able to survive massive failures, even a whole continent going offline.
And the second is locality.
Geographic locality. You want to keep the data physically close to the applications and the users who need it. That's how you minimize latency for the end user.
So the app developers get to make a direct trade-off here. They can choose their replication configuration based on what they need more. Is it latency or is it resilience?
They do. It's a direct choice. If your application is all about low read and write latency, you might go for, say, 3 to 5 replicas all inside a single geographic region.
So all in North America, for instance.
Exactly. That gives you maximum speed, and you're still protected if 1 or 2 data centers fail. But for the really critical stuff, like the F1 advertising backend we'll get to later, they chose cross-continent replication.
Spreading it out much wider.
Much wider. 5 replicas spread across the U.S. That gives you the highest possible availability against, huge correlated failures.
All right, let's trace how an enormous system like this is actually managed. We have to start at the very top with the universe.
The universe is the highest level. It's a complete functional spanner deployment. And historically, Google has only run a handful of these. There's like a test universe, a dev prod one, and then the big production-only universe.
And inside a universe, you have zones.
Right. And the zone is the key unit of physical organization. It defines your administrative deployment, your failure isolation, and it's a potential location for where your data replicas live.
So a zone is basically a data center, or maybe a piece of one.
You can think of it that way, yeah.
No.
Zones contain the actual computers, the resources, and to keep this whole ecosystem running smoothly, Spanner has these crucial control plane components. These often run as singletons for the entire universe.
The two big ones being the universe master and the placement driver. The universe master seems pretty straightforward. It's like a centralized status console.
It is. It's the big dashboard. You use it for high-level monitoring, for debugging. But the placement driver, that's where the real operational magic is happening.
Because its job is to balance the data.
Its job is to balance the data across the globe to meet two often conflicting demands: load balancing and meeting those application-defined replication constraints we just talked about.
How dynamic is that? I mean, say my application needs a directory of data moved from the East Coast to Europe because all my users suddenly shifted. How fast does the placement driver react?
It operates on a timescale of minutes. It's constantly polling the data servers, it's analyzing the current load, and it's initiating automated data migration across zones.
Without a human in the loop.
Completely automated. If your app suddenly gets popular in Asia, the placement driver will proactively move data or maybe add new replicas to zones near that traffic. It's all about maintaining performance and availability without manual intervention. That's what makes it a truly global, adaptive system.
Okay, so that brings us down from the control plane to the data plane, the components that are actually in each zone.
Right. So in every single zone, you have a zone master. Its main job is resource allocation. It's the thing that assigns data shards to the individual span servers.
And then clients need to find that data.
And for that, you have location proxies. These are critical. When a client wants a piece of data, it asks the location proxy, hey, which span server is holding the shard I need?
And that leads us to the span servers themselves. The workhorses.
The workhorses. These are the machines that actually store and serve the database content. And they're deployed in huge numbers, anywhere from 100 to several thousand per zone. They're handling all the reads, the writes, the transactions.
So this whole nested hierarchy.
Yeah.
Universe, zone, span server. It lets Google manage this massive global thing while still keeping local isolation and control at the zone level.
Precisely.
All right, let's drill into what's actually running on those span servers. That software stack is where the engineering really shines, providing both traditional database features and distributed resilience. I think we need to look at this from the bottom up.
Definitely. At the very bottom, I've got the tablet layer. It's conceptually pretty similar to a Bigtable tablet, but there's a critical difference in its data model.
Okay.
A spanner tablet implements a mapping. Its key.string timestamp.int64 maps to a string value.
And that timestamp.int64, that's not just some piece of metadata. It fundamentally changes what the store is.
Oh, absolutely. I mean, Spanner is inherently a temporal multi-version database. Every single write is tagged with a system-assigned timestamp. You're not just overwriting data, you're creating a new version of that data tied to a specific point in globally consistent time.
And where does that state actually live?
Physically, the state of the tablet is stored in B-tree-like files and a write-ahead log, and all of that persists on Google's distributed file system, which is called Colossus.
Colossus, right? The successor to the original Google file system, GFS. Okay, so we have storage, but now we need replication. That brings us to the Paxos layer.
Right. Each one of those tablets runs on its own dedicated Paxos state machine, and the multiple copies of that tablet spread across different zones, they form a Paxos group. Spanner leans very heavily on Paxos to provide synchronous replication and consistency inside that group.
But implementing Paxos globally, where your replicas could be hundreds or thousands of miles apart, that's a huge latency challenge.
Yeah.
Standard Paxos needs multiple round trips just for one write. to get a quorum incomplete.
And that's where one of Spanner's big implementation innovations comes in. They use what they call pipelined Paxos.
Okay.
Traditional Paxos has this geometric dependency. You have to wait for the acknowledgement of one phase before you can even start the next proposal. This just kills your throughput when you have wide area network latency, maybe 50 milliseconds one way.
So how does pipelining break that dependency?
It uses a concept from Lamport called a multi-decree parliament. So instead of waiting for one vote to finish before you propose the next decree, the leader can pipeline multiple decrees at the same time.
It sends out proposal N+1 before it even gets the full response for proposal N.
Exactly. It amortizes that high latency cost across many transactions, and that drastically increases throughput. The key, though, and this is crucial, is that even though the voting and the acknowledgments are all happening out of order, the decrees are applied to the state machine in strict sequential order.
So correctness is guaranteed. You're just maximizing your use of the network.
You got it. And they also use long-lived leaders, the least leadership for about 10 seconds, which further cuts down on the overhead of constantly electing new leaders.
That efficiency is just essential. I also like the read optimization they have. If a replica is sufficiently up to date, reads can just go straight to it, which avoids the leader becoming a bottleneck for all your read traffic.
And then once you move above that replication layer, you get to the consistency control mechanisms. And these live only on the leader replica.
Okay, let's start with the lock table.
The lock table is there to enforce strict two-phase locking, or 2PL. You have to remember, Spanner supports long-running transactions, things that could last for minutes. For that kind of workload, something like optimistic concurrency control, it just performs terribly because you get so many conflicts.
So they went with old-school two-phase locking.
They did. The lock table is mostly volatile, it maps key ranges to lock states, and it's the first line of defense against conflicts happening inside a single Paxos group.
But what about when a transaction needs to touch data in different Paxos groups? That's when you need the transaction manager.
Yes, the transaction manager is there to support distributed transactions, and it specifically implements the two-phase commit protocol, 2PC. If a transaction involves multiple Paxos groups, the transaction manager on one of them acts as the coordinator leader, and it orchestrates the whole thing.
And unlike the lock table, the state of the transaction manager, that must be durable.
Oh, absolutely critical. The state of the transaction manager, so the prepared state of any distributed transactions, that has to be stored in the underlying Paxos group. It has to be replicated and fault tolerant.
Okay, so we have the machinery for consistency and replication. Now, how does an application actually structure its data to take advantage of this sharded world? This is where the directory and interleaving concepts come into play.
Right. So the fundamental unit of data management in Spanner is the directory. And a directory is just defined as a set of contiguous keys that all share a common prefix. This is the unit for which an application specifies its replication config.
So I'd say for this directory, I want 5 replicas, and I want them in these specific zones.
Exactly. It gives the placement driver something concrete and manageable to move around. But even more powerful is how applications can define locality using the interleave in declaration. This lets you create a data hierarchy.
Can you walk us through the performance benefit of doing that interleaving? It seems really important.
It's a game changer in a sharded system. Imagine you have a customers table and an orders table. If you declare orders interleave in parent customers, what happens is that all the orders for a specific customer will share a key prefix that's derived from that customer's ID.
So the customer's main record and all their orders are physically stored together.
Potentially within the same directory, on the same set of machines. In a sharded system, that is just invaluable. Without interleaving, if you wanted to get a customer and all their orders, you might have to make network requests to dozens of different span servers all over the world.
But with interleaving, it becomes a local read on a single Paxos group,
which drastically cuts down your latency and your network traffic. It's a masterclass in sharding efficiency. You're organizing your storage based on how you access the data, not just some arbitrary distribution.
And we know this distribution isn't static. You mentioned placement driver is moving these directories around all the time using this background task called movedir. The sources mentioned that these directories can be pretty big, like 50 megabytes or more. Moving that much data atomically sounds like it would cause really long pauses for clients. How did they get around that?
They made a very conscious design choice. They prioritized availability over transactional purity for the move itself. So MoveDeer is not implemented as one giant 2PC transaction.
That would be a nightmare.
It would lock everything up.
Yeah.
Instead, it streams the data in the background from the source Paxos group to the destination group. And while this is happening, clients can still read and write to the source. The system only uses a final, tiny little transaction at the very end.
To do what?
To atomically move the last bit of data and update the metadata pointers between the two groups, which redirects all the future traffic. It's a really practical design that minimizes the outage window to just milliseconds. So ongoing client operations are barely affected, even by these huge maintenance tasks.
We have the architecture, the data structures. Now we have to talk about the fundamental problem of global consistency. Time. I mean, why isn't the network time protocol NTP, which we use everywhere, good enough for Spanner?
Well, NTP can synchronize clocks pretty well, often within a few tens of milliseconds. But its fatal flaw, at least for strong consistency, is that it gives you no guarantee. It gives you no measure of its error bound.
So you don't know how wrong it might be.
You don't. And when clocks drift or networks add latency, you just can't be certain whether an event a machine in Tokyo recorded actually happened before an event a machine in Berlin recorded, especially if the times they report are close.
And TrueTime solves this by just acknowledging that uncertainty. It treats it like a geometry problem, not just a synchronization problem.
Exactly. The TrueTime API, specifically the ttd.glo call, it doesn't return a single point in time, dollars. It returns a tinterval dollars, an interval, earliest, latest.
And the error bound, epsilon, is half the width of that interval.
Right. And the guarantee is ironclad. The absolute physical time of that API call is mathematically guaranteed to fall somewhere inside that earliest, latest interval.
This bounded uncertainty. This is the geometric constraint that lets Spanner enforce that external consistency and variant globally. You know the exact window of uncertainty, and you can programmatically wait for it to pass.
Without that guaranteed bound, there is no way at all to ensure that if my transaction T1 commits before your transaction T2 starts in the real world, that T1's timestamp $1 will truly be less than T2's timestamp $2. TrueTime provides the necessary proof.
But achieving such a tight bound globally requires some incredible infrastructure. What makes up their time synchronization network?
It all relies on extremely accurate and redundant physical clocks. They use two main types of reference sources. First, you have GPS receivers, which are installed in most of their time masters in each data center.
GPS is super accurate.
It is, and it's readily available. But GPS is also vulnerable to correlated failures, like local radio interference or signal spoofing.
And that's where let's be honest, the dramatic component comes in. The atomic clocks.
Yes, the Armageddon masters. These are high-stability atomic clocks, and they're strategically placed and physically isolated from the GPS masters. Their failure modes are completely different. They're incredibly stable, but they can drift over the long term.
So by using both, and by physically separating them across different locations, different power grids,
they mitigate the risk of a simultaneous correlated failure taking out their entire time source.
Okay, so every single span server machine needs a way to talk to these super stable masters and keep its own local clock in sync.
That's the job of the time slave daemon. It runs on every single machine in the fleet. And this daemon is continuously polling multiple masters, local GPS masters, faraway GPS ones, and those isolated Armageddon masters.
How does the daemon decide which of those time sources to trust? There must be outliers.
It uses a really clever bit of distributed systems logic. It's a variant of Marzullo's algorithm. Marzullo's is designed to find the smallest interval that intersects with the most input time intervals.
So it's looking for a consensus.
Exactly. The daemon collects the time reports from all the masters and uses the algorithm to detect and just discard liars masters that are reporting a time interval way outside the credible consensus window. This makes sure the local clock is only synchronized against trusted sources, which maintains the integrity of that epsilon bound.
After you sync, though, the local clock inevitably starts to drift. How is the epsilon value calculated and presented dynamically?
The total uncertainty, epsilon, is basically the sum of the time master's uncertainty and the local clock's drift. And Spanner conservatively bounds that local drift at 200 microseconds per second. So if the daemon polls the masters every 30 seconds...
You can accumulate up to 6 milliseconds of drift.
Right, and the daemon is constantly broadcasting this increasing uncertainty.
So if you were to graph it, what would that look like?
It creates this sawtooth pattern. When the time slave daemon successfully pulls the masters and syncs the clock, epsilon drops dramatically, often down to around 1 or 2 milliseconds. Then, over the next 30 seconds, epsilon slowly climbs as the local clock drifts, reaching a max of around 7 milliseconds before the next sync pulls it back down again.
The average being around 4 milliseconds.
Typically, yeah.
And this is the core trade-off of the whole system. Correctness demands that they report epsilon conservatively, maybe even making it a bit bigger than it needs to be just to be safe. But performance demands they keep epsilon as tiny as possible.
Because a larger epsilon forces Spanner to wait longer, which directly impacts your transaction latency. That is the geometric constraint of the entire system.
Okay, so true time gives us this measure of time. But the concurrency protocols are the rules that actually use that measure. And these algorithms are built on two foundational invariants.
They are. The first one is the monotonicity invariant.
Simple but critical.
Very. It just says that Paxos writes within any single group have to get monotonically increasing timestamps. And this has to be true even if the Paxos leader crashes and a new one takes over.
And how do they enforce that across leader changes?
They do it by restricting the leader to only assign timestamps that fall within the duration of its current leader lease. So when a new leader takes over, it knows it has to assign timestamps that are greater than any time that could possibly have been assigned during the previous leader's lease.
And the second invariant is, well, it's the crown jewel, right? The external consistency invariant.
This is the global promise. If transaction $1 commits before transaction $2 starts in the absolute physical timeline, then the system guarantees $1 will be less than $2 screen. And true time is the only thing that makes this possible across widely dispersed Paxos groups.
Let's get into the details of the read-write transactions protocol. It uses that strict two-phase locking we talked about. The key true time rules are applied during the commit phase by the coordinator leader.
Right. The first rule is the start rule. When a commit request hits the coordinator, it has to calculate the commit timestamp. And the rule is that size$ has to be greater than or equal to tt.9
So if Spanner is assigning a timestamp that is guaranteed to be in the absolute future relative to the moment the coordinator saw that commit request.
Exactly. It uses the upper bound of the uncertainty, tt.noensev, now latest.leather, to make sure the assigned timestamp can't be temporally ambiguous with when the commit request arrived. This is essential for upholding that external consistency ordering relative to other transactions that might start later.
And then comes the famous step, the commit wait rule. This is the moment Spanner pays the bill for consistency.
This is the critical geometric step. The coordinator leader has to make sure that the transaction's effects, the committed rights, are not visible to any clients until the time's definitely passed. It has to wait until the condition TT after is confirmed to be true.
And because $, was assigned based on tt.now, the leader has to wait out that entire uncertainty window, which means waiting at least $2 epsilon owned.
That's the one. If your average epsilon is 4 milliseconds, the system introduces a mandatory wait of at least 8 milliseconds, just for the clock uncertainty to resolve itself and guarantee the ordering. This commit wait, which can go up to 14 milliseconds if epsilon is large, is the single biggest measured cost of providing synchronous global external consistency.
That wait is the price of admission. I know they try to overlap this wait with the network latency of the Paxos commit protocol, but it's still there. It's the fundamental overhead.
It is, but the beauty of it is the proof. By making sure setsilon is less than the absolute commit time of T1, which they do with the wait, and making sure the absolute start time of T2 is less than 202, which they do with the start rule. They achieve global transitivity. They get strict ordering across the entire system.
Okay, now let's talk about reads. Because if every transaction has to wait for time to advance, read-heavy workloads would just have terrible performance. This is why Spanner puts so much emphasis on snapshot transactions for read-only traffic.
Right. Snapshot transactions are lock-free. They operate at a system-chosen timestamp, ZERI, and since they don't acquire locks, they don't block writes. That is a massive performance gain.
And they have a really nice performance optimization if the read is just confined to a single Paxos group.
Yes, for a single site read, Spanner can do something clever. It sets DORI to last TS, which is just the timestamp of the last committed write that was applied to that specific group.
And since last TSCS is already in the past,
there's no need to wait for TTS to be true. The read can happen immediately without any global synchronization.
But if it's a multi-site snapshot transaction, a global read?
Then you have to go back to the conservative externally consistent method, they set surety dollar, the latest down, and they might have to wait for time to safely advance before they can execute the read, just to make sure they see all prior committed transactions from all groups.
This brings up the concept of safe time. How does a replica know that it's safe to serve a read for some given timestamp? $2.
So every replica tracks a value called say savado. This is the maximum timestamp for which it is absolutely certain it holds all committed data. A read at timestamp dollar can only proceed if $T is less than or equal to $T.
And if it's not?
If the read timestamp to dollar is greater than safe, the replica has to stall that read. It has to wait until its own safe advances past to dollar.
Okay, and the $T is a minimum of two different values, right?
Yeah.
It reflects two different sources of potential uncertainty.
Exactly. It's T-Paxos safe. PTM, T-Paxos safe, is the timestamp of the highest Paxos right that the replica has applied. And since Paxos guarantees in-order application, if a replica has applied decree number N, it knows it has all the data up to timestamp safe or no-order.
But what if the Paxos group is an idle? If no writes are coming in, does Paxos say just stop advancing? Because that would block any reads that need freshness.
They have a graceful solution for that. It ties back into the leader leases. The Paxos leader maintains a mapping, min next TSN, which is the minimum timestamp it could possibly assign to the next Paxos sequence number, none dollars.
And because the leader holds that 10-second lease.
It has temporal control over that interval, so it periodically advances min next TSN for future sequence numbers. A replica can then safely advance its own T-Paxos safe to min next TSN, even if no new writes are arriving. It uses the leader's guaranteed lease interval to keep time moving forward.
That's a really elegant solution to that idle leader problem. So what about the other value? TTM safe, why is that needed if Paxos is already tracking the applied rights?
TDM safest is all about the state of prepared transactions in the two-phase commit process. When a transaction enters the prepare phase, its state is indeterminate. It hasn't committed, but it might.
So it's Schrodinger's data.
It's exactly Schrodinger's data, and you can't let readers see that uncertainty. If a reader was allowed to read past the prepare timestamp of an indeterminate transaction, they might see data that's about to be overwritten, or they might miss updates that are about to commit.
So TTM say prevents that.
Right. It's calculated as the minimum prepared timestamp of all currently prepared transactions minus 1. This forces any reads at later timestamps to block until those prepared transactions are resolved, either committed or aborted, which ensures the reader only ever sees a fully consistent, resolved state.
Okay, finally, let's talk about what TrueTime enables for massive maintenance operations. These non-blocking atomic schema change transactions. Historically, rolling out a schema change across a massive database, it's just a nightmare. It requires downtime or these complex multi-stage migrations.
Bigtable's original model often required global freezes for schema changes, which is just. It's unacceptable for a modern, always-on global system. Spanner completely avoids this by using the global time reference from TrueTime.
How does assigning a future timestamp solve a global coordination problem?
Well, the schema change transaction gets assigned a timestamp, $2, that is explicitly in the future, let's say 10 minutes from now. Right. And this future timestamp is globally registered during the prepare phase.
And because TrueTime provides a globally meaningful frame of reference.
Reads and writes across the entire universe implicitly synchronize with $2. If an operation comes in with a timestamp before $, it just executes against the old schema. If an operation comes in with a timestamp after $, it blocks. It waits until time has actually arrived and the change has been applied everywhere.
The genius of that is that it's using time itself as the locking mechanism. Once the physical clock passes $2 and the change is applied, the whole world instantly switches to the new schema without some massive global transaction lock.
It's proof that if you can master time, you can master distribution. I mean, this mechanism allows for atomic, non-disruptive schema changes across millions of servers. That is arguably one of the most powerful maintenance features Spanner has.
Okay, we've laid out the theoretical framework.
Great.
But now we have to confront the practical reality, which is the performance cost of all this global consistency. Looking at their micro-benchmark results, what does the data tell us about the latency drivers?
The data immediately points to the cost of that $2 epsilon commit wait rule. In their single replica test, the total write latency was about 14.1 milliseconds. And of that, roughly 4 milliseconds was directly attributable to the commit wait.
Wow. So nearly a third of the latency in a local write is just purely paying for the global consistency guarantee.
That's the cost. But the scalability of writes across continents is surprisingly good. When they went up to 5 replicas spread out geographically, the mean write latency only increased a little to 15.4 milliseconds.
Why so little?
Because the Paxos commits all happen in parallel, and the transaction only has to wait for the slowest member of the quorum to acknowledge. The increase is sublinear.
But on the other hand, snapshot reads, which are lock-free, they scale almost perfectly linearly.
No, they fly. Because a read only needs to hit one sufficiently up-to-date replica, your throughput scales directly with the number of replicas you have. A single replica got them about 9.7 thousand operations per second. 5 replicas delivered 46.8 thousand.
So it's a powerhouse for read-intensive, globally distributed apps.
Absolutely. It leverages all the available resources really efficiently.
But if we look at transaction throughput, how many writes it can handle per second, that trend completely reverses.
Write throughput actually goes down as you add replicas. And the reason is simple. The Paxos work increases linearly with the number of replicas. More replicas means more messages, more voting, more network overhead, and that forces the right path to bottleneck, even with pipelining.
So it's that classic trade-off. More availability for more replicas costs you write throughput.
It does.
The decision to support general two-phase commit was also a bit of a risk. A lot of modern distributed systems try to avoid 2PC, they just assume it doesn't scale. Did the benchmarks justify their choice?
They really did. The benchmarks showed that 2PC is entirely viable for the kind of workloads Spanner was built for. The mean latency stayed remarkably low, around 33.8 milliseconds, even with up to 50 participants.
50 different Paxos groups in one transaction.
Right. It's only when you push towards 100 participants that the coordination overhead starts to get prohibitively high. So this confirms that Spanner provides a practical, usable transactional feature. It spares developers the agony of trying to manage distributed state by hand.
Let's talk about what happens during failures. I know Figure 5 in the paper showed the impact of losing a Paxos leader. What are the key takeaways from that availability testing?
Well, first, the system's design really proved its fault tolerance. Killing a non-leader zone had basically no impact on throughput, which is what you'd expect. A leader soft kill, where the leader had time to gracefully hand off its lease, that only resulted in a tiny, temporary 3–4% dip in throughput.
But the leader hard kill, the abrupt, unannounced crash, that tells the real story about recovery time.
The second the leader hard crashes, throughput just plummets almost to zero. And it's not because of data loss, it's because the system has to wait for the leader lease to expire.
And the default lease is 10 seconds.
It's 10 seconds. So the system only recovers after that dead leader's lease interval passes, which allows a new leader to get elected by the quorum. Then, throughput rapidly recovers back to normal, but it proves that the Paxos leader lease duration is the direct, unchangeable dictator of your recovery time. It's a guaranteed 10-second window of reduced availability.
Let's pivot to the stability of the true time infrastructure itself. I mean, how often does that vital epsilon bound actually spike?
So the engineers found that while the core integrity of the system is really strong, they noted that bad CPUs was 6 times more common than bad clocks. The performance is highly sensitive to external factors. The data shows a pretty significant tail latency vulnerability.
Tell us about the measured epsilon spikes they saw.
Well, the base epsilon is usually stable, but performance isn't always predictable. They saw that network congestion could temporarily raise the uncertainty bound, which causes a transient increase in commit wait latency. More dramatically, they logged one incident where routine maintenance required them to shut down 2 time masters at one data center. That single event, it caused epsilon to spike and stay elevated for about an hour.
Across the entire system.
Across the entire system. An entire hour of elevated latency globally just because 2 machines were taken offline for maintenance. It's a vivid demonstration of how that global consistency cost is directly coupled to the absolute stability of the time infrastructure.
It's a direct consequence of the trade-off. If you want a stronger guarantee, you have to be transparent about the underlying uncertainty. And when that uncertainty goes up, your performance suffers in proportion.
Exactly.
Now, let's bring this all home with the F1 case study. This is Google's massive advertising back-end rewrite, and they were the first major production client to bet their business on Spanner. Why did they abandon their old system?
F1 was originally built on manually sharded MySQL. They were managing tens of terabytes of data, and their sharding scheme was fixed. All the related data for a customer was assigned to one specific shard. The biggest operational nightmare for them was resharding.
How bad could that process get?
It was catastrophic. The last major resharding event they did took 2 years of intense effort. It involved coordination across dozens of engineering teams and massive manual oversight just to make sure data was migrated with integrity.
2 years.
2 years. The process was so painful and disruptive that F1's primary motivation for moving to Spanner was the promise of automated, non-disruptive global data movement, the placement driver and move deer. They needed the database to handle scale migration dynamically so they would never have to go through a multi-year manual process again.
And beyond just the operational scale, what transactional needs did F1 have that something like Bigtable couldn't satisfy?
They needed absolute consistency for financial operations. They needed complex transactional semantics, and they needed consistent reads across arbitrary parts of the data. That's something eventual consistency just can't give you. Spanner's strong consistency let them build features that were critical to their business, like consistent global secondary indexes. They knew that any read would be guaranteed to reflect the latest write, no matter where in the world the data or the client was.
Okay, so with all those advantages, what were the actual production latencies that F1 saw? Because this is where the theory meets messy reality.
The results were pretty startling. The mean read latencies were acceptable, around 8.7 milliseconds, but the standard deviation was enormous, 376.4 milliseconds.
Whoa!
Yeah, and commit latencies were high too, from 72 milliseconds for single-site transactions up to 103 milliseconds for multi-site ones.
Wait, a 376 millisecond standard deviation on reads. That sounds like a major inconsistency in performance. It almost defeats the purpose of guaranteeing a 4 millisecond consistency cost. Why was that variance so high?
This is a fantastic probe into the system's real-world fragility. They traced that specific high standard deviation back to the infrastructure layout. So F1 was replicating across 5 zones, but the Paxos leaders were spread across 2 data centers, and here's the key. Only one of those data centers had machines with solid-state drives, SSDs. The other was still using slower traditional hard drives.
So the variance wasn't a clock problem at all. It was an I/O problem that got amplified by global replication.
Precisely. When a Paxos leader that was on an SSD-equipped machine failed, the new leader was often elected on one of the slower spinning disk machines. And that change in disk performance significantly increased the latency tail for both reads and writes. This case study just demonstrates that in a globally synchronized system, your performance ceiling isn't just dictated by the speed of light or the precision of atomic clocks. It's dictated by the physical characteristics and the homogeneity of the weakest link in your repetition chain.
That's a powerful lesson. The consistency guarantee holds true, but the performance the user actually experiences is constantly vulnerable to these underlying hardware differences.
Spanner is, without question, it's a monumental achievement in computer science. It successfully integrates these high-level database features, full relational schemas, transactions, SQL, with the massive scale and fault tolerance of global distribution.
And the architecture itself, relying on that span server stack, the Paxos groups, and the directory abstraction. That's what enables the dynamic scale and efficient sharding.
It does.
But the indispensable core, the algorithmic breakthrough, it remains the TrueTime API. By formally bounding the inherent uncertainty of global clocks and enforcing that crucial $2 epsilon commit weight rule, Spanner achieves external consistency. It gives application developers the one guarantee they desperately needed all along.
Which is real-world temporal ordering across the globe. That guarantee means developers can trust that if they saw event A happen before event B, the database timestamps will confirm that fact, globally. That level of intuitive consistency. It just changes how you build global applications entirely.
We know that Spanner's performance right now is limited by the infrastructure's ability to minimize that clock uncertainty, to minimize epsilon. And the engineers noted they don't see any insurmountable obstacle to getting epsilon below 1 millisecond.
Right now, that price of global consistency, that $2 epsilon weight, it typically costs between 4 and 14 milliseconds. But if global timing technology is improved, maybe using deeper space references or significantly better oscillators and polling systems, and that consistency cost could be reduced to, say, 2 milliseconds.
What revolutionary real-time globally transactional applications would that unlock? And how quickly would that shift the entire landscape away from systems that are forced to rely on eventual consistency, that potential reduction in the geometry of time? I think that's the ultimate next challenge for distributed systems engineering.